It's a pleasure to be back here for a second year. Thank you all for coming, and for those online as well. I think you can ask questions using a link underneath the video if you're watching live, so do that. I thought I'd start back in the early days of Gresham. We had the privilege in the college to be following in a line of professors that goes back to the late 16th century, and I've become slightly obsessed with trying to find out what my predecessors would have said. Presumably they had different jokes than me. They certainly had a different universe to describe, but I'd like to believe that one of the things that were talked about in the first set of Gresham astronomy lectures, or the first few sets, was an observation of a new star in the sky, which appeared in 1604. This was a remarkable event. Such things have been recorded in the past, but they're rare. And for astronomers still arguing over whether the centre of the solar system was the sun or the earth, and for an astronomical world that tended to see the heavens as a fixed realm of unchanging beauty, the appearance of a new star was a distinct and remarkable event. It's marked on this map, which was made by the great pre-telescopic observer and theorist Kepler. It shows the constellation of Ophiuchus, which is the 13th constellation of the zodiac, for reasons we can discuss another time. It's the serpent bearer. And then down at the bottom there's a star marked with N for nova, new star. Kepler's initial approach to this star, which had been seen by others, as I said, was scientific. He checked it wasn't moving by measuring its position against those of nearby stars. Measurements he made to about a precision of about 100th of a degree. Remarkable, given that he was only using the naked eye. He saw that it didn't seem to have parallax. It didn't seem to move as the Earth moved around the Sun, or vice versa. And so he realized it must be distant. It's one of the distant stars. It's not like an asteroid or a planet. And initially, it was as bright as the brightest planet, and it remained observable for about a year as it slowly faded. So this was clearly a remarkable thing. Kepler, it was a chance to think hard about astrology, because this was around the time before astrology and astronomy had diverged. He was interested, and wrote about in his book De Stella Nova, the new star, he was interested in trying to pin down when Christ was born, an event marked in the Bible by the appearance of the Star of Bethlehem. He was trying to observe a conjunction of planets, Jupiter and Saturn, within what he called, rather wonderfully, the fiery trigon, the three constellations of the zodiac which are associated with fire. And the appearance of this new star alongside that conjunction, he felt must be a significant event. And he ended up going back to a similar conjunction in 7 or somewhere between 5 and 7 BC, and saying there must have been a new star then as well, and that would have been the Star of Bethlehem. So most of the book he writes about this object is about that astrological process of deduction. But it's also about trying to understand what these stars are. Part of the argument at the time was that if these stars are indeed bodies out beyond the most distant planets they're known, out beyond Saturn, then given their observed size on the sky, they must surely be very big indeed. And this was considered by opponents of the new heliocentric Copernican astronomy to be ridiculous, that you'd never have such large bodies in the universe when you only have nice planet-sized things around here. It seems extravagant. And so a bit of the book is about that. What he doesn't do is offer a physical explanation for why this new star has arrived. We now know that it's what we would call a supernova, an event that's caused by the death of a massive star. To understand supernova, you have to realize that stars, though we think of them as constant and unchanging, are unstable. Our sun and the other stars are in a state of delicate balance between the gravity that tries to pull their material together and energy generated by the nuclear reactions at the core, which generate the heat and the light that we get from the sun, which push outwards. And these two things are in equilibrium, balanced against each other. And so when something changes, when, for example, a massive star runs out of fuel for those nuclear reactions at their center, the equilibrium is disturbed, the star will collapse, gravity wins, And slightly paradoxically, that collapse causes an explosion and a scattering of material. And in that explosion, new nuclear reactions can happen, producing heavier elements. And what we see as a supernova is the decay over the course of a year or two of the elements that are produced in that catastrophic explosion at the end of a massive star's life. Now, Kepler didn't know any of this. This has all been worked out over the course mostly of the last 60 or 70 years. But the thing we haven't had to aid us in this process of deduction and study is a supernova that was as close as the one that Kepler saw in 1604. The closest we've got is this. This is a picture from 1987, from late February 1987, of a patch of the southern sky. It shows a bright star in front of a star field and nebulosity. And that bright star was just like Kepler's, a new star in the sky. It was discovered by two astronomers in Chile, Ian Shelton, a Canadian professional astronomer who was observing this part of the sky and knew it well enough that when he saw the image come up on the observatory computer screen, he realized there was a star there that shouldn't be there. He ran next door to the observatory and he told them that he'd discovered a new supernova, only to run into Oscar Duhalde, a Chilean astronomer, in fact, a telescope assistant, somebody responsible for the facilities on the mountain, who said that he'd noticed it too because he'd been outside and looked up. This is the easiest, if you're quick, this is the easiest astronomical discovery of the last 40, 50 years, because you go outside, you look up, you have to notice that there's a new star there. Half an hour later, a team in New Zealand reported the same thing, and actually, it was discovered in photographs taken by many other people in the previous 24 hours, people who hadn't known the sky well enough to notice that it was different. It had to be a supernova. It was actually in one of the Magellanic Clouds, satellite galaxies of the Milky Way. And so this is the closest supernova since the invention of the telescope. We haven't had one visible within our Milky Way, though there have been two that we should have seen that no one saw, for reasons I can answer questions about later. So we have this local explosion. It was visible for about a year. It faded slowly. We actually have images of the sky, this part of the sky before the explosion, and we were able to see that the progenitor, the star that produced it, was a blue supergiant, which at the time caused a lot of excitement. This is an unusual class of star. People didn't know that they were going to go supernovae in this way. But it was only a few years later where we saw the after effects of the supernova. Here's the same image of the sky, the same part of the sky on the left, and then I've zoomed in on the right. And what you can see there is the rings that have formed around this explosion from 1987. Here's the sequence over the course of 20 years or so. The supernova itself is in the middle. You can see that it's fading over time. And this ring is material that was there already, perhaps given off by the massive star in the last few years or few centuries before it exploded, lit up by the energy produced by the supernova. Now, as you can see, something strange happens. The supernova itself happened in 1987. By 2003, we suddenly got a new brightening of this ring of material. And what's happened is that it's not just light that's spreading out, material has been thrown out from the center. And it's spreading out and it collides with this ring, which is about about a light year across, nearly 20 years, or a bit more than 20 years after the supernova, and causes this brightening, which then is now steadily fading. So what we can see is this one exploding star now has an effect on its surroundings. And this is one reason we care about these supernovae, not like Kepler because they are of astrological importance, because they influence their surroundings within the galaxy. If you map our surroundings in the galaxy, if you map the sun's neighborhood and you plot the density of gas around us, you find, so the colors here represent the density of gas. We're right in the middle of this diagram. That circle is 100 parsecs, which is just over 300 light years across. So this is our local neighborhood. Remember, the galaxy is tens of thousands of light years across. You find that we live within a bubble. And that bubble was caused by supernovae, which happened in the last 10 to 20 million years. So we can say something about the history of our neighborhood by looking at this. And one of my favorite things is that this observation, which is purely astronomical, this is celestial cartography. This is old school astronomy. We're just mapping where stuff is. Can be combined with observations of elements here on Earth, where we find rare isotopes of, for example, iron, rare types of iron that were created when cosmic rays from those supernovae 10, 20 millions of years ago hit our planet. So supernovae have this profound effect. And one of the things that they do is they can compress the gas that they run into, just as we've seen with these bright patches here. And when that happens, they can trigger a new they can trigger a new stage of star formation. We can watch that happen. On the edge of this local bubble, about 300 light years away, there is a star-forming region called the Taurus molecular cloud. This is a region within it called TS Tauri. Astronomers, as I've said in almost every lecture so far, are terrible at naming things. So instead of some nice romantic name for the star, this is TS Taur B and A. A is the bright star on the right, and then at the top there's a sort of hamburger of material, which hopefully you can see. There's actually a newly formed star buried within that dusty disk. You can't see the star because of the dust which blocks its light, but we can see its effects. We can see its light, and in blue you can see jets of material shooting away from that new star. This is something that young stars often do. It's caused by the magnetic fields of the star, which catch up the material and send it shooting into its surroundings. You can see that it has an effect on the leftover gas that's surrounding the star. This is a complicated picture. This is the story of one star-forming region, but you can trace it all the way back to a supernova that kick-started the process. And the reason that we can talk about these things in such detail, and that I could show you pictures that, frankly, are, I think, interesting enough and beautiful enough that I should probably just put them up and leave the stage, and you can have half an hour enjoying them, is because we launched a telescope into space. Both the images of supernova 1987A that I showed you and TS Tau, though not the hand-drawn map of Ophiuchus, all of those things come from the Hubble Space Telescope, the most famous scientific instrument in the world. And that is what I want to talk about tonight. But perhaps we should start at the beginning. I think I should explain why we want to put a telescope in space. And if it seems obvious to you, then you should have deep pockets and a willingness to fund a space agency, because it's difficult still to launch something into space. We can build a bigger telescope on Earth. The Very Large Telescope, for example, in Chile, said we were bad at naming things, or the Extremely Large Telescope, which should have its first light within about the next year or so. I mean, the Extremely Large Telescope is big enough that its dome, its enclosure, is like a football stadium. The telescope itself has a mirror 39 meters across. That doesn't fit even in the massive rockets that SpaceX are building with an eye on lunar exploration. We can build bigger and, frankly, better telescopes on Earth. It's also, as we'll discover a bit later in the lecture, easier to fix a telescope if it's on Earth, even if you have to go to Hawaii or Chile, than it is to go to low Earth orbit or even further away. So we have to be driven to do this. We have to want to go to space. And there are two main reasons. The first is that though I appreciate the fact that I can breathe, the Earth's atmosphere is my enemy as an astronomer. It causes stars to twinkle. Now, I know that's a delightful nursery rhyme, but it's also really annoying. The effects are quite dramatic. I'm a huge fan of the work of an astrophotographer called Steve Brown, who takes images like this. So this is a set of images of the brightest star in the sky, Sirius. What he does is he takes video of the star, and then he takes individual frames. What you can see very clearly in this image is that the colour of the star appears to be changing as Steve watches it. Now, these aren't real changes. What's happening is that the light, as it passes through the atmosphere, is distorted by what's in the atmosphere and by the movement of the Earth's atmosphere. It causes different wavelengths of light to be bent differently. And so we see this dramatic twinkling, coloured twinkling, which you can see yourself. Sirius from the UK is always low to the horizon, so it's a particularly good example. Further up, you're looking through less of the atmosphere and things are less good, but this effect persists wherever in the sky that you look. You can also see the effect more clearly on one of Steve's videos. So if I play the video, this is just Sirius over time. You can see that change in colour, but you can also hopefully see that the shape and the size of the image of the disk is changing over time. That's the effect of the Earth's atmosphere. In fact, if it wasn't for the Earth's atmosphere, there should be a pinpoint speck. The stars are far enough away that they should only ever appear as point sources. But because of the atmosphere, they appear as a disk. A phenomenon, incidentally, that misled people like Brahe and Kepler, the early 16th century astronomers, to think that what they were seeing here was the true size of the star. They thought they were measuring how big Sirius and the other stars are. There are solutions. One can build into your telescope what's called an adaptive optics system, a mirror that moves rapidly, maybe 50 times a second, to counteract this motion. But then you have to measure this motion really precisely, and it's a very difficult task at most wavelengths and for most objects. The conclusion, put wonderfully by James Obdam, who was the Hubble program manager during the difficult days of the 1980s when it was being built, said that trying to do stellar observations from Earth is like trying to do bird watching from the bottom of a lake. I think that's very right. You could tell, perhaps, if you're lucky, that birds are there, but you're not really going to get a clear picture of them. The second reason to go into space is that we miss out on most of the light that the cosmos is sending us. We see visible light that our eyes are sensitive to, but our eyes are sensitive to those wavelengths of light because they get through the Earth's atmosphere. If you go much outside that range, and in particular, if you want to look at what's called the ultraviolet, with wavelengths shorter than we can see, then light from the cosmos doesn't even reach the ground. So to get a full picture of the objects that we're studying, you need to get beyond the atmosphere. And as an example of that, here's Jupiter from the ground. This is with the 8-meter Gemini telescope in Hawaii. Familiar features, the belts of the planet, the storms, the great red spot, the giant storm several Earths across that has been raging for at least 150 years, and which may now perhaps be dying out. But if I switch to the ultraviolet in an image from Hubble, you'll see that it looks different. Different features are prominent. Others appear or disappear altogether, and the great red spot has gone dark. And that's because high-altitude haze in Jupiter's atmosphere blocks the light from the warmer spot beneath. And so we learn, by switching to the ultraviolet, we learn about Jupiter's atmosphere. So for these two reasons, both because we want to get away from the horrible atmosphere and so that we can see at wavelengths hidden from us, it seemed obvious that we should put a telescope into space. The idea, I was surprised to find, goes all the way back to the 1940s, to a report written in 1946 by an astronomer called Lyman Spitzer. So this is more than a decade before even the simple Sputnik satellite was launched into space. And yet, people were dreaming of what you could do if you could put a telescope up there. In fact, Spitzer was arguing that we should take the 200-inch telescope that had just been opened on Mount Palomar in California, an enormous thing welded together with bolts, and put something like that into space. That was the 40s. The idea hung around for a bit. NASA, in particular, got distracted by putting one small step onto the lunar surface. It wasn't really until the 1970s, when they were looking for a new purpose for the space program, that the idea of a space observatory started to be taken seriously. When it was, a design, this is the final Hubble design, but people happened on this pretty quickly, was arrived at pretty easily. Hubble reuses the body of a fairly common spy satellite, we now know, although I'm not sure that was known at the time. It has a primary mirror, light comes in, it bounces off the primary mirror, it hits a secondary mirror, and that then feeds back a bank of cameras and instruments at the back. It's a design that is still the most common form of telescope you might buy if you're an amateur astronomer. There's a folded up arrangement of mirrors. At the time, in the 70s, it was called the Large Space Telescope. Nothing as grand as Hubble. Although if we're talking about now, I have to tell you that there is a Canadian mission which reused a tiny telescope to do star tracking, and it's called the Hubble Space Telescope. maybe sometimes we get the names right. So the Large Space Telescope was funded by NASA, but almost instantly went over budget. It was the subject of much political argument in the 1970s, which you could read about in the histories of the thing. But I wanted to point out particularly that in the most vicious of those arguments in 1974, when Congress was threatening to cancel the project entirely, the justification put forward by astronomers led by Jesse Greenstein, who was at Caltech, wasn't that this would be practical or that this would create jobs on Earth, though both of those things are true, nor did they make the argument that it would be a technology driver. That's really striking because these days we tend to argue that you do big science projects because you might accidentally develop new technologies. And that happened with Hubble. This bank of cameras at the back was the first project to use what are called CCDs, the electronic cameras that exist in all of your phones and which drove the move away from film in the 1980s. They were developed really on a large scale for the Large Space Telescope and for a couple of planetary missions. So we all benefit from Hubble, but that's not the argument that was used. What the astronomers said was we should do this because the Large Space Telescope will open up new vistas for humankind and open up new vistas for the human mind to contemplate. I like a world where that's a winning argument. That's fun. Anyway, there were more arguments. The telescope went over budget many times, but it launched on the space shuttle on April the 24th, 1990, and here it is a few days later being released into space. Now, the existence of the space shuttle was crucial because the shuttle was designed to be a fully reusable spacecraft. The original plan was that something like 100 to 200 shuttle missions a year would fly. And so what the astronomers had envisaged was they'd have their telescope in space, and if something happened, if a new supernova went off or they changed their mind about what observations they wanted to do, you would just send the astronauts up with a new camera, swap it out, and you might visit the telescope every month. It's almost as good as having to go to Hawaii to fix your telescope. It was designed to be serviceable. That's the point, with shuttles flying on demand. But by the time the telescope launched, the disaster of the destruction of the Challenger spacecraft in 1986 had made it clear, amongst many other problems, that shuttles were not cheap and that it was hard to go. But we got Hubble into space, and the results have been incredible. I was talking about massive stars that might go supernovae, and one of my favourite Hubble images is this one. This is an image of the star Betelgeuse, or sometimes called Betelgeuse. You'll know it's the top left star in the familiar constellation of Orion. You can remember where it is because Betelgeuse is a corruption of the Arabic name for the star, which translates as armpit of the Great One. Which there's a real theme about naming things going on this evening. Betelgeuse is an enormous red giant star. It's nearing the end of its life, and you'll often see it quoted as the next star to go supernova. It will, at some point in the next million years or so. I've already promised Gresham that when it does, I'll come back and give a special lecture. When it does go supernova, it will be bright enough that you'll be able to see it with the naked eye at midday. Just to give you some scale. People are occasionally worried we're far enough away that we'll be safe, but it will trigger a burst of star formation and affect our region of the Milky Way. But what we can see in this image is that it's not just a dot. This is the real image of what those previous astronomers thought they were getting. It's huge. We're actually seeing the real size of the star here. It's nearly as big as Jupiter. So if you placed it in the solar system, Earth would be inside it. And it, like all stars, exists in this delicate balance of pull and push, of gravity versus nuclear reactions. And its outer layers have been described as the closest thing to something that's still nothing. It's an incredibly low-density environment, which explains why it faded dramatically just 4 years ago when dust produced in the star's atmosphere blocked out the light and we lost some of its brightness, something we followed with Hubble. Betelgeuse will go supernova, but not all stars do. Smaller stars, those from a little less big massive than the Sun up to about 8 times the massive as the Sun, end their lives in a less dramatic fashion. They don't ever explode. What happens instead as the Sun starts to lose its fuel in about 4 or 5 billion years, we should anticipate that its outer layers will just be released, will escape from the star's gravity and will be shed into the cosmos, forming what's called a planetary nebula. They're called planetary nebulae not because they've got anything to do with planets, but because through the eyepiece of a small telescope, they look like the disk of a planet. And they're spectacularly beautiful when seen with Hubble's sharp vision. From the ground, these are very difficult things to study. They're small and difficult to see. From space, when you have the resolution of the Space Telescope, you see wonderful things. This is the Ring Nebula. The dot in the center is next to the remnant of the star. You can see there's the ring and then this sort of structure here, these tendrils, where you can see the gas is being stripped away by material coming from the center. And before Hubble, this is what people thought all of these objects would look like. Complex, but essentially round and beautiful. Turns out they come in a variety of different shapes. This is the red spider. There are more good names coming. This is a nebula whose form is driven by a central star, which is one of the hottest in the galaxy. It's hundreds of thousands of degrees Kelvin. And the ripples you can see are waves 100 billion kilometers high, driven by winds spreading out from the center of gas that's heated up to about 10,000 Kelvin. We've got the butterfly, another hot central star, and my favorite is the red rectangle, which is an object that's so confusing that it's had whole conferences devoted to it. If you know why this thing looks like this, please see me afterwards and we'll write a paper together. The story that's emerging, and the reason I've shown you a few of these, and there are many more you can go and look, is that when you look more sharply, you see that things are more complicated than we expect. So rather than sometimes when we talk about how science proceeds, you would expect to get more data with Hubble, we'd get a better understanding of how planetary nebulae work and we can put them away and finish that book. Well, we do have a better understanding of how they work, of how complex winds and the central star produce things like the red spider. But what we've actually gained is more questions. And this is something that keeps happening with this telescope. But I've skipped a bit of the story. Remember that the point of putting Hubble in space was to get above the Earth's atmosphere, to get away from the twinkling that's caused by the atmosphere. To take advantage of that, Hubble's mirror had been machined to ridiculous precision. If you blew up the entire mirror to the size of the Earth, the biggest imperfection in it should be about 6 inches. Almost nothing. And so this is a precision machine designed to take precision images. And yet when the first images came down to Earth, they weren't that impressive. On the left is an image from a Hubble-sized telescope in Chile. On the right is one of the first images that Hubble sent back from space. And if you squint and you believe and you want to be convinced, I can probably tell you that the one on the right is a sharper image than the one on the left. At the top, there's maybe a bit more definition in that double star. But really, this is pretty disappointing. This is not what people were expecting. It became obvious almost straight away that there was a problem, not with one of the cameras on board, perhaps lived with, Hubble had several instruments, but with the main mirror. But I've just told you that it was made to a very precise shape. So the puzzle was, how could the main mirror have something wrong with it? All sorts of investigations started, all sorts of groups from NASA to astronomers to people running the telescope spread out across the US to go back through all documents to look at how things had been done. And remarkably, several of those groups found at the company that had made the mirror that the rig they'd used to test what they were doing was still there. And a crucial piece of that rig was a rod that was designed to make sure that the test equipment was exactly the right distance from the mirror so that everything would be right. And it turned out that that rod had been placed in a position that was wrong by 1.3 millimeters. Something they should have known at the time. It was actually an error caused by chipped paint on the end of the rod. Now, the company and the engineers there had ignored the results of less sensitive equipment that told them there was a problem, and they'd ignored a recommendation that they double-check before you launch your telescope into space. But the rig was there, and people were able to work out what had happened. And so the mirror had been precisely fashioned into exactly the wrong shape. This is a PR disaster. NASA, we should point out, by the way, that the European Space Agency and the Canadian Space Agency were partners on the project. We Europeans had provided the solar panels, and there was also a problem with them. They were flexing weirdly, causing the telescope to shake, but wasn't as big a problem as the American one. So we'll talk about theirs. So what do you do if your mirror is out of shape? Well, one solution is that you can still do spectroscopy. You can still do science when you split the light that you receive into its constituent wavelengths and make a graph. And you can use this to understand, say, what planetary nebula are made of or how distant galaxies are. It's good science, and we would have made use of such a telescope, but it's not what the taxpayers had paid for. Astronomy is driven by images. Science is driven by images. It's not just PR. And so a telescope that couldn't take sharp images might as well have been sitting on the ground. Hubble had been designed to be repaired. NASA could launch a shuttle with new cameras, which would have sort of internal corrective optics, contact lenses, to correct what was seen. But that would have involved going back to the politicians and asking for approximately $500 million to fix the telescope that you built that was broken. Also, it would have taken about 15 years for a telescope that was projected to last about 20. That doesn't work. And this was a problem that occupied the team for a long while. They were stuck. There was a meeting in Germany of several of the teams working on this. And at the end of a very hard day, an engineer called Jim Crocker went back to his hotel room and wasn't the first American to be mystified by European plumbing. I promise there's a reason I'm telling you this. In particular, he'd never seen normally he was used to American showers tend to be built in, and you have a faucet up here, and you hide all the plumbing because you don't want to think about that stuff. This is one of those showers that's just attached to a rod on the wall, and then it's fed by the tap, right? We all know what we're talking about. And he was there trying to sort his shower out because it had been folded down and placed against the wall. He lifted up the shower head, and then he pulled it out. And then he did that again, and he thought, we need a shower head. Because he realized that if you could take one of the cameras that Hubble had out of the barrel of the telescope, put in a new thing, and then have something pop up with corrective lenses, you could correct the light that was going to all the other cameras with that one simple device. So that's what they built. It's called CoStar. Here it is. It looks more like a set of dentist tools than a shower head. But each of these little lenses, and there were 11 of them in all, were correcting the light that was going to one of the instruments. And on the right, these are the astronauts installing a new camera in 1992 that fixed Hubble's visions. Between these two instruments, this big problem was solved by the most complex shuttle mission that was flown at the time. There were 10 separate spacewalks, and they had to do all sorts of things to try and get the telescope back to its best, but it worked. We suddenly got sharp images of the cosmos. Here's before and after of a nearby galaxy. You can see the difference. The one on the left is interesting. The one on the right is beautiful and also tells us more scientifically. And so from here, Hubble produced a set of greatest hits. My own favourite memory is when the comet Schumacher-Levy 9, seen here as a string of pearls, these dots underneath Jupiter. This was a comet that was ripped apart by Jupiter's gravity and which slammed over the course of a week into the giant planet's atmosphere. Hubble showed us the scars that it left, these bruises which were produced by comet hitting the atmosphere of the planet, something we'd never seen before in human history. I remember watching this as a kid and getting online at school to see these images come in each day, and I was delighted in preparing these features to find in a National Geographic documentary video, and I want you to remember this is 1994, of the science team responsible actually seeing these images for the first time. So here they are. I said it was 1994. I just think this is very enjoyable. What I like about it is you can see astonishment, you can see joy, you can see excitement, and for the guy in the yellow jumper, you can see somebody who's trying to work out what on earth is going on. all of which are perfectly valid scientific reactions. And I invite you to enjoy that. I'm going to put this online. You can enjoy that. And, I think for fancy dress parties, I think coming as this group of people would be great. But you can really see what having a telescope that can take images does for you. I think it's really exciting. I'm not going to talk today about galaxies. Hubble revolutionized the study of galaxies other than the Milky Way, particularly in its beautiful images of merging galaxies like the mice shown here, and in the Hubble Deep Field, which I talked about last year. But I want to talk a bit about what Hubble's done for the science of star formation. We've talked about star death. Let's talk about star birth, how stars like the Sun and larger stars like Betelgeuse come to be. There's a textbook version of this story that's basically been the same since the 60s. And I have a literal textbook photo to show you. Don't worry too much about the details, but the story is that you have a cloud of gas and dust somewhere in the cosmos. The dust blocks the light from all the other stars in the galaxy, and so it becomes cold. When it's cold, gravity becomes important, and this cloud can collapse under its own gravity. The density at the center of the cloud increases, and it gets to the point where you have nuclear fusion. The star lights up. The light and heat and the winds that it produces, perhaps through those jets that we saw earlier, clear away most of the material, and the remnants that's left forms a planetary system like the Sun. So that was the basic picture that we've had for a long time. And it's still, if I wanted to give a 2-sentence long lecture on how stars are formed, I would say that and I would get off stage, because what Hubble showed us, and what much work since has shown us, is that if you have this textbook picture fixed in your mind, you miss the glorious complexity of what's actually going on. This is the Carina Nebula. It's my favourite place in the galaxy, as viewed by a set of Hubble observations stitched together. It's a place where there was a burst of star formation about 300 million years ago, and where a second burst is underway. And the longer you look at this, the more you pick out all sorts of interesting details, shapes we never imagined, and things we never thought we'd see anywhere in the universe. What you can see here is the influence of... This is the thing that's missing from that textbook picture, is that we're missing the fact that these things don't form in isolation, that as soon as you form one star, its light affects its surroundings. You can see this cluster of stars down here, which formed about 300 million years ago, have created a bubble around themselves, creating a space in the center of the gas and dust of the nebula. Over on the left, there's a bright source, which is one of the most famous objects in the sky. It's a star called Eta Carina, and it looks like this. It doesn't look like a star. This is a star that, actually, we think there are 2 stars in the middle there, with a combined luminosity of about 5 million times the Sun. It's 3 million years old. It's recent. And in the early 19th century, it suddenly brightened up and became one of the brightest stars in the sky. It then faded so that you couldn't even see it with the naked eye. It rebounded a few times, and it's now just about visible with the naked eye. But with Hubble's vision, it's revealed that these stars are undergoing traumatic mass loss, that they are losing material in these lobes, and at the center are preparing to go supernova. But you can see in the context of the Carina Nebula that star over here, this is Eta over here, is sculpting itself a bubble. And you can see on the right-hand side here that there's a region where new stars are being formed as the hydrogen gas and dust is compressed by the winds that come from that single star. It would be possible to spend a career studying this image. I know people who are working on it. It's a beautiful thing, and it shows the complexity and inadequacy of our simple textbook models. What we've learned from Hubble is that we need more complicated stories to tell. Star formation with Hubble studied in Carina is also in the most famous image of all, I think. This is the Pillars of Creation, the Eagle Nebula, a phrase which was used in the scientific paper that described this object, the Pillars of Creation, actually comes from an 1857 sermon by a London preacher called Charles Spurgeon. But these days you see this on everything from T-shirts to coffee mugs to, I think, Liberty sell leggings with this pattern, if you're interested. And what was particularly exciting about this object is when you zoom in at the tips of these, extrusions, these pillars, you see these little tiny features. Each one contains a protostar, which will go on to form something rather like the Sun. We got to watch star formation happen in real time. And people are still studying this. We have new toys. Hubble taught us that an observatory in space was useful. We've now launched others, like the JWST, which launched a few Christmases ago. Now, JWST is bigger than Hubble, but it's sensitive to infrared light, to wavelengths longer than the optical. And so when it looks at the pillars, on the left is the Hubble image, on the right is the JWST one. They're about the same resolution. We get to see within the pillars, we see the colder regions, the gas and dust which is about to become stars. And so Hubble has inspired a fleet of new spacecraft, and we're still dreaming of more and more telescopes that we might build. There's a telescope launching in a few years called the Roman Observatory, which will basically do a sort of Hubble-like job, but will scan the whole sky. But we've already started work on a project that was called LUVOIR, but is now called the Habitable Worlds Observatory, HWO, which will show us distant galaxies in new detail. This is a galaxy seen as it was about 8 billion years ago, as seen with Hubble. With options for the new telescope, we'll get to study it in detail. We'll get to study the atmospheres of nearby planets. And even in the solar system, this is Pluto, not a planet, by the way, but still interesting. This is Pluto as seen by Hubble, and then with options for these future telescopes which have bigger mirrors, the images are almost as good as we got from the New Horizons space probe that flew past Pluto a few years ago. We'll get to watch weather on Pluto. So we have options for future telescopes. We have a legacy of incredible images from Hubble. In fact, that archive, which is open to anyone to look at or browse or use, is now responsible for more papers each year than the telescope itself. The archive is a more valuable scientific instrument than the working telescope. And the telescope is just about hanging on. It's in a new mode of operation. It hasn't been serviced since more than 15 years ago at this point. And so it will probably last another 5 or 6 years, perhaps as many as 10, and then it will be deorbited. We're going to send a spacecraft to go and get it and ensure it burns up over the Pacific Ocean. It's an ignominious end to a beautiful instrument which has left us with some startling pictures of the cosmos. I want to finish with this. This is my favourite object. This is the Orion Nebula, our nearest star-forming region. And again, you see gas sculpted by the presence of bright young stars. But the thing that we've learned from Hubble is that a great observatory does give the human mind new vistas to contemplate. But the thing it hasn't done is reduce the number of questions that we have about the cosmos. In fact, because it's a truly great observatory, it's vastly increased them and created the need for more telescopes and more mirrors in the sky. Thank you very much.